This is part 4 of the calorimetry tutorials, and here I'll definitely be finishing the chapter. Just the last concept is left, the concept of latent heat that I just told you. Now I've taken this sample from the last tutorial. You have this conversion over here from solid to liquid at 0 degrees Celsius. You're providing it heat. I've denoted it as Q, and this is your sample. Say it has a mass m. Now you're providing it energy Q, and the mass is m, and it goes from solid to liquid in a certain time. Now for that substance that we're talking about, that we've taken in this example, there's something called the specific latent heat. Its symbol is L, and it's just like specific heat capacity. For each substance, you're going to have a specific latent heat, and that is basically how much heat energy do you need to carry out this conversion for a unit mass of that substance. So specific latent heat for a substance is equal to Q. Q, we're only talking about this part of Q that is used in the conversion. We're not talking about here or here. Only the one used from solid to liquid over there. And we divide this by M. So this gives you a specific latent heat. Now, if you're given a specific latent heat of any substance and you're given its mass, or instead of mass, you're given the heat energy required, you can easily tell the other variable that is left out. Say you're given L and you're given M. So from this relation, you can see that L into M is equal to Q. So if you're given that the mass of this substance is so much, and its specific latent heat of vaporization is this much, you can tell how much heat energy would it need to get converted fully from liquid to gas. And I said latent heat of vaporization, there's also latent heat of melting. So you can guess that solid to liquid, we're talking about melting, liquid to gas, we're talking about latent heat of vaporization. So that's all there is. And again, just like the last section, there are a few more reasoning questions. For example, ice and a few other substances have a very high specific latent heat. So for those, they've given certain scenarios and certain reasons why certain processes occur, which are due to this. So you can look through those. Those are pretty important, but I can't explain much over there. If you understood this concept of latent heat, you'll understand it yourself. And the same thing as the last section, you can replace this Q if you're given a power and a time that's electrical, and you can replace it by PT. Your formula will remain the same. Q will still equal to ml, but instead of Q you write P into T. That gives you your energy. And now in your books again, they've given a long formula, a long calculation for finding something. I don't know what this is, but you don't need to do all this. Again, if you understood how this whole thing works, you'll be fine over here. Also, another thing, when you're calculating this part, the formula that you'll use is mc delta t. When you're calculating this part over here, from solid to liquid, you're going to use Q is equal to ml. And from 0 to 100, you're again going to use mc delta t to find out what your heat energy is. So just remember that whenever you have a change of state from solid to liquid, liquid to gas, or vice versa, you always need to use ml. When you're just increasing temperature, your state remains the same. Use mc delta t. So I'm just going to do one very quick question. And remember that in this chapter, I think the mistake that I made with this was that I just looked at the theory bit of it. I didn't really do much of the numericals. So that's where I lost, I think, 4 marks in my board exams. You should definitely do this. So I'm just going to erase all this before I move on to the question. It's a very small question, and I've chosen it because it involves both concepts. MC delta T as well as ML. So this is from your textbook's concise physics. So how much boiling water at 100 degrees Celsius? If you want to refer to the question in my edition, which is 2012 edition, it's on page 281. Boiling water at 100 degrees Celsius is needed to melt 2 kg of ice, so that the mixture, which is all water, the mixture you get when you mix these two, say you have, I'm going to try and draw it just so you get an idea. Boiling water, so I'm just drawing a few vapors. It's at 100 degrees Celsius, right at the melting point, and you have 2 kgs of ice. When you mix these two, what you should get is all water. It shouldn't be at 100 degrees Celsius. It shouldn't be at any other temperature. It should be at 0 degrees Celsius, that's given in the question. Now, what you've been asked, you've also been given the specific heat capacity of water, which is 4.2 joule per gram Kelvin, and you've been given this is specific heat capacity of H2O. I hope you still remember what that means. And specific latent heat of ice is 336 joules per gram. This is the information you've been given, and you've been asked how much boiling water at 100 degrees Celsius do you need. So now one thing is clear, you're going to take this boiling water at 100 degrees Celsius. You're going to mix it with 2 kg ice at, you're going to assume that it's going to be at 0 degrees Celsius here. And you want so much of this, let's say m grams of this, such that your final mixture will all be water at 0 degrees Celsius. So using heat loss equal to heat gained. Now heat loss will obviously be by the boiling water because that's at a high temperature. So MC delta T, where M is for the boiling water, delta T is equal to MC delta T. I'm not writing numbers like 1 and 2 over here. I'm sorry, not MC delta T here. Actually, what's going to come here is ML. If you look at it, we just need to convert all of this to 0 degrees Celsius water. Right now it's 0 degrees Celsius ice. So I said right before this, you need to use ml in these cases. So just put in the values. M into, we've been given the specific heat capacity of water, that's 4.2 joules per gram Kelvin. Also notice it's grams, so we're going to convert our mass. Our mass is going to be in grams. So 4.2 over here. Our delta T is 100. We need to bring it all the way to 0. So 100 is equal to m into L. Now the mass we've been given 2000 grams, that's 2 kgs, and 336 joules per gram. So since both are in grams, that's fine. So 2000 into 336. And I'm not doing the calculations, but what you should get in the end is m is equal to 1600 grams. You'll get in grams because we've used grams everywhere, and you can convert this to 1.6 kg. There are many more questions like these, and I suggest you do all of them from the book. I did it, but I did it way before the exam, so I really didn't know a lot when it came to the exam. So I suggest you shouldn't make that mistake and do all of them, because these do come as 4-mark questions, sometimes in section A as well. So definitely don't leave this out, and I think you'll be fine in this chapter.